Recording has
So
started.
hello everybody. All right, hello everybody. Welcome back to the second episode of Error Correcting Erik, a podcast series where we go on a journey of discovering the philosophy of David Deutsch together. Uh, I'm a bit sick today, so my voice is a bit crackly, so apologies about that, but that shouldn't prevent us. So for those who weren't there, in every episode, we explore a chapter of the book, and we are now at chapter 2, Closer to Reality. And maybe Thomas, you can give a brief introduction before we dive into the concept. The second chapter, what is it about?
So closer to reality. I have to say, I re-listened Brett Hall's uh, uh, podcast series about it as well, to see what it was about. And how about maybe a better way to get into it is maybe for you to tell me what you think it's about.
Hmm.
Um,
Yeah. So the author tells a story that he was looking at pictures of stars and galaxies, and from the little stories that he tells, how they used to do it in the past. For me, I can distill two very important concepts of that. For the first time, actually, I start to understand like what's error correcting. What does that mean? Which is, of course, the title of this podcast. And in the book, it is explained that so David is looking at pictures, and there are little specks of light on those pictures. And back in the day, they didn't know if it was a star, a speck of light, or it was a galaxy. They didn't know. So they had to do some extra analysis. They need to do good estimations. They need to do additional calculations. And for example, if the edge of the speck of light was very fuzzy, it was likely to be a galaxy. But the thing is that they didn't know. They needed more data, they needed more sophisticated equipment, measurements to be able to determine it. So that's where the idea of error correcting comes from. We don't know what the truth is at the moment, and we constantly need more knowledge to be able to improve those, to improve our conclusions.
mhm, mhm,
And for me, that's in a stark contrast with the way we are brought up, with the way we are educated. I believe we're brought up in a very linear way, from an authoritarian point of view. From as a moment where children were being taught in school, we're being taught like this is the way it works. Like the Mandalorian. This is the way. This is how it works. This is how you should do it. This is how you should complete a task. And I don't think a lot of people are challenged to think critically, yeah,
mm,
and are challenged to think for themselves and to think in creative ways and in open ways. So I like to say it's a very linear way of thinking, and the error correcting way of thinking is really the philosophies. Look, you don't know, and you constantly need to make less and less errors, and that doesn't mean that you're wrong or that your ideas are wrong. No, it's just inherent in the nature of reality. And knowledge is a powerful tool in there to
mm.
become a little bit better, a little bit smarter every day. So that's the first major concept that I got out of it.
So to just tag on there, there is no um, different ways of thinking. There's just thinking. Um, Even when you're going to school, even throughout that system of what you described as linear thinking, you're you're still doing the same thinking. Um, it's not like your brain, you know, you switch a gear and your brain starts doing something else, right? It's just that the environment in which um, you model your own way of thinking changes. It's like, let's say you are a religious person and all of a sudden you've come to understand that you know God, there isn't a God, and I've been living 20 years of my life under the impression that there is kind of this almighty being that does everything and has all the power. And then let's say your mental model shifts from that to a more scientifically based one. it's not like your brain has changed, your ideas have changed. So that's the important thing to note, is that there is just thinking. And then you can process good ideas or you can process bad ideas. Same as if you go to the gym, you can work out the right way, you can work out the wrong way, depending on, but it's still the same muscle that you're training, right? It's not that your muscle somehow has shifted into a different thing. So to come back to the galaxy thing, right? So I also have it open here, the second chapter. And so he says that they mounted one of the plates, the photosensitive plates, and you have to look through it. And let me actually share my screen here as well so that we can look at that together. So here it is. So this is kind of the picture that they had in the book. So the point of this chapter really is to say that without a explanation of what a galaxy is, that can be anything. You can be looking at ants, you can be looking at whatever the thing is that you think it can be based on your best guess. So that's what your brain is doing. It's guessing something based on the knowledge you have, based on the framework you have. So let's say you grew up in a time where there was no even a concept of a galaxy. If you would see this, you would think, oh, maybe it's, I don't know, pepper, or maybe it's ants, whatever the thing is. So it requires a very sophisticated, let's say, knowledge accumulation for that brain to be able to look at this and go, oh, these are galaxies. And actually, based on certain laws that we have come to understand, based on the distance of galaxies, based on the luminosity of certain stars, etc., we can actually deduce that they are either that far away or yada yada yada. So, but notice how much knowledge one needs before you can even start the let's say the analysis part of that picture. So it's more than, you said we need more analyses, we need more data or something, but um without a explanatory model to say this is a galaxy and we're looking at a galaxy, and a galaxy consists of what? Because, can you hear me? Yeah. And the galaxy, like, what does that even consist of? What are we looking at? Like, before, if you took a picture of the sky, the ancient Greeks, or I forget which society it was, they thought they were candles behind the cloth, right? So imagine that you show this to those people, they're going to say, oh yeah, that's just those are the candles that are burning far away in the sky. But they never thought that there was actual distance behind it. They thought it was just a cloth with candles being lit behind it. So Deutsch says very very profoundly, there is no such thing as theory free observation. You cannot observe without imposing your explanatory framework to it. So in the sense that we error correct through testing things with reality. Also, abstractions can be tested. But in this case, the point he's making here is that, let's say you're this scientist, you're a astrophysicist, right? And you're looking at this thing and you get so excited because so you're coming to this, right, with your explanatory framework of, I know what galaxies are. I've actually taken a picture with my sophisticated, the most sophisticated machinery that mankind has seen up until then. Millions of data processors are taking all the light in, and they're doing everything that they've been programmed to do, right? And then all of a sudden you go and you see this and you go, oh my God, so exciting. I think I discovered a new galaxy. And you go, oh my God, this could be the next biggest scientific discovery of all time. and you start doing the math. You start, you get all excited. So that's the brain, right? The brain of the scientist is getting super excited, hyped up. And then 2 seconds later, you go, oh, it was actually just a smudge. So you go from thinking greatest discovery ever to maybe I found another galaxy. Maybe your brain as an astrophysicist goes to thinking, oh, maybe there's other people on that galaxy, and then you start to wonder, are there other astrophysicists looking at our galaxy right now and pondering of our existence in that other galaxy? All these ideas, all these romantic notions, of what is possible, start to kind of, the optimism seeks and seeps through to me. But then you go, and then in some, that's what they call the Duham coin thesis, and I'm not entirely sure on the name, but it at least rhymes with it. And it has to do with the fact that any observation you've done could just be a systematic error in your machinery, or in the application of the maintenance of the machine, in just it's a fluke. They once thought, for example, that they noticed faster than light speed travel once in CERN. They thought they had observed that, and I remember at the time when that happened, I was in college, and the news took it and ran with it very excitingly, like, oh, Einstein has been proven wrong, blah blah blah. And then, like, a couple of weeks later, it was like, oh no, it was actually just an error. They found one of the cooling system ventilation things had malfunctioned, and therefore the data, right, that it gave was wrong. So it took me as well a long time to really comprehend the because this is one of the most profound chapters as well of this whole book. It's a shorter chapter, but they call Deutsch, they call him his writing knowledge dense. So there's so much knowledge that he sneaks into his sentences that you need to kind of unpack for what it is, and you need time. But really, the sentence, there is no such thing as well, sorry, it's better to say what it is. So every observation is theory laden, and theory laden means you're applying a theory to it. And the let's say the proof of this is everywhere, because we have writings of how Romans looked at things, how Greeks looked at things. And if the book of nature was really just something that we need to read from to then literally, like, look and, oh, um apple falling, apple there, now apple there, how, why did Newton not get to relativity theory? Why did he have to go through gravity? And then Einstein later came with relativity theory, which was a different theory. um so if the book of nature was just something to be read, why didn't the ancient Greeks read it back then? They had the same universe out there, they had the same reality, yet they didn't do it because they didn't have the knowledge yet to do it, because their culture didn't have the knowledge yet. So culture also, carries knowledge throughout. Um, More than DNA that we have also carries knowledge throughout, but our ability to share cultural knowledge actually accelerates our ability to make progress, because we can do it a lot quicker than DNA evolutionary cycles would need. So, and I'll pause in a second here, but this was so profound to me because I equally, so what you call the way that the linear thinking in school that we were taught is what they call empiricism. So the empirical mindset was one of, data rules all, and that's that. And it was a useful philosophy in contradiction to what was previously a very monotheistic culture. Before the Enlightenment, or the more critical scientific way of thinking that came through the Enlightenment, um, people thought in more dogmatic ways. They thought, it's because God said so. It's because God wrote this book and it's in there, and the pastors are saying this, right? So it was necessary to show all let's say the hardline Christian people at the time, to show that, hey, look at the data, it contradicts the book, the scripture. So how can you contradict what you're seeing with your eyes versus what this God is, somewhat supposedly telling us? So empiricism was an improvement to the monotheistic culture that was reigning. So again, that's the error correcting part, right? Empiricism is better than a religious dogmatic culture, but the empiricists' dogma, let's say, then becomes data is God, and before, God was God, and then data becomes God, and then you'll see that now as well, like mathematics has become almost godlike because there's some kind of supposed objective reality out there. So there is an objective reality out there, right? I'm not gonna. There is something out there. It's just that our knowledge of that thing, which is called the epistemology, and the ontology, is the actual thing. So again, like Newton and Einstein saw the same moon, right? It was still the same moon going around. They had just very different explanatory models of why the motions were doing what they were doing. So I think that is a critical thing that Deutsch is trying to get through here, is that whatever you think you're observing in your so-called data it could well likely be a smudge of the finger that your assistant at the university accidentally put on your plate. And does that make sense? I'm gonna pause for a second.
Yeah, absolutely. If I understand your point of view, so let's dive deeper into the moon orbiting the Earth. What you're saying is, like, Newton and Einstein, they had the exact same data. They saw what the moon did. So if there would be like a universal truth, like reading the book of nature, be able to derive it from the data, like anybody would be able to do it. But that's not what happened, what you say. So Newton saw it, he looked at the data, and he derived a set of explanatory knowledge, some explanatory model. And then Einstein came along. Let's assume he had the same data, and then he derived a different model. So that's, I think, your point with, oh, it's not just having the data and then reading the data and then there you have it. No, it is.
But
it is.
notice,
if you want,
notice the. And sorry for interrupting, but notice the what's the word, contradiction that you're bringing to the table. You're saying that he read a different data set and he then had a different explanation model for the data. But
no, the same data. So
right, but
because they saw the same thing.
Right, but so I think a better way to phrase it is the reality out there is the same for them.
Yeah, exactly.
But the data, whatever that means in this context, you could say Newton was maybe plotting. I don't know. Again, like you only have data when you have a model to apply it to. Without there is no such thing as an observation without the theory coming first, because Newton said, "Oh, it's a force of gravity." That was nowhere in the data, that force of gravity. He saw something happening in reality, and then he explained it through an idea that was the gravity. So it sometimes gets tricky in language, because if you mean by they had the same data as in they had the same reality out there, then yes, I agree with you. They had the same data. But
that's what I meant.
Okay.
Most likely Einstein had more data because there was more sophisticated equipment and measurement and so on. So I would rephrase it like that. It's the same reality. Let's call it the same observation that they can make themselves, but different theories arise from that, right? That's kind of what you're saying, if I understand it correctly.
No, yeah, but not entirely, because it comes from the brain, the theory. It doesn't come from the observation. The theory is invented in the brain, and that's also what Einstein does. Then he doesn't he literally invents it. It didn't exist before, right? Like space, like relativity theory, like literally didn't exist as a piece of knowledge before he literally created it into existence. So it's more profound than that, actually. You can't get you cannot say that the data came first, because yes, there's a reality out there and you're testing your model against reality. But Einstein, it didn't have anything to do with better equipment, because it had to do with they weren't the technological revolution there. Let's say from going to a better telescope wasn't what led Einstein to his new discovery. It wasn't an increase in programming ability. It wasn't, or sorry, in speed, in processor speed of computers. It wasn't any of those things that made him come to relativity theory. His brain came up with a new idea, a completely fresh new way of looking at it, which was space-time curvature. And then he went to test it against reality. And then he saw, hey, the predictions of my conjecture, my new idea, actually tracks better, more accurately to reality than Newton's model does, if that makes sense. So it took me a very long time to get those things out of each other, but you cannot you can, even as what you're doing now, right? The sound waves that you're hearing, the visual things that you're seeing, like there are people out there that have, let's say, a certain chromosome, and they have, they don't see color that well as like, colorblind people. They see reality differently because their brain interprets it differently. So they literally have a different model. They have a different color scaled model than we do, than the non-colorblind people. So even through that, you can kind of, it shows that you don't interpret free of it's kind of a circle way of thinking, because I want to say you cannot interpret without interpretation. But but I understand what it's a bad argument. The circle argument is never a good one, the circular one. But what I'm trying to say is, without an idea of what you're looking at, whatever you think the data is meaningless. If you don't have a concept of a dog and you see something and you've never seen a dog before, then your brain will start to think of ideas like, what could it be? Is it some kind of cat? Is it maybe you've seen cats before, right? Maybe is it some kind of cat? No. Is it some kind of horse? No, that's not you. It's like, no. And you look at what you know in your thing is a horse. Like, no, that's not a horse. Like, what is it? Like you're starting to guess for it. You're not deducing dog from the observation. You have to guess, and then you test it against reality, and then based on your interaction with reality if it's a good explanation or not.
It's a very interesting way of looking at it, and it makes a lot of sense. But let's dive a bit deeper into how Einstein then came to his conclusion, because I was under the assumption that because knowledge is built upon knowledge is built upon knowledge, and you always increase it. I actually had that thought the last time I was in a plane. We were flying to Asia, and we were in that plane, and of course you had 12 hours of nothing to do. So I started thinking about how the plane works and how there is so many crazy, complicated mechanisms there. It's like, how can you invent such a thing? But then, you bought me the book, and that was actually the first time I was reading the book. It was on the plane. And then I got to think, well, it makes a lot of sense because it's built upon years and years and years of knowledge. We start with a very simple plane made from wood and paper, or I don't know, and you build upon that. So nobody just invents a plane as it would be today out of nothing. You start from something small, you add knowledge on top of that, and then you end up with a very complicated system, such as a modern plane. So that's how I thought, um,
but what's the process through which you're adding knowledge? That's the question.
Yeah, exactly. Because now we come to the point, and that's a bit how I think like scientific knowledge also increases. You start from a piece of knowledge, you add a little bit upon to it until suddenly.
What's that mechanism? How does one add knowledge? What is the adding of knowledge? What is that thing?
Error correcting, of course.
What is error correcting? I mean, error correcting you can see as the thing solves a problem better than the thing before. Yeah. So like relativity solves the motion of planets, the problem of the motion of planets. It solves it better than Newton did. So it's more useful, let's say, than Newton.
Yeah. Well, so I always thought that indeed it was just more data, more knowledge, more sophisticated stuff, not only. But for as far as I understand it now, that's not per se the case. That's not necessarily required, or more data, more knowledge, more sophisticated equipment does not necessarily lead to an expanded model. No, it is more the new way of thinking and then testing in it. So not data first, but ID first. I think that's kind of what you're trying to say.
So again, yes. So the short answer is it's creativity, and the add-on there is we have no idea how it works. We don't know how the human mind is able to do that, and that's okay that we don't know. But we do know that again, the empiricists like to say you just have to read the book of nature, and out comes your thing. But then again, like why didn't the ancient Greeks then have relativity 5,000 years ago because they had the same planets to look at, right? So, but you are right. We stand on the shoulder of giants to look even further. So yes, we accumulate through our culture and through our sharing of memes, and in our memes, then that knowledge is packaged, and memes is a later chapter in Deutsch's book here, The Beginning of Infinity. But the mechanism through which knowledge is literally created is unknown to us. And that's okay. Let's call it creativity, like what Einstein did when he literally got a new model for relativity was a creative endeavor, right? Because it didn't exist before, else it would have existed before. So let's call it in formalization, it is the equation, right? That's the formal depiction of the explanation. But the explanation of space-time as a thing goes beyond the formalism. It is a way of explaining the context of the observations, and not the other way around. You cannot observe your way to a new explanation. You have to, yes, you use reality because we are in that reality, and again, we don't know how the brain does that, right? But the brain goes, that's odd. That doesn't make sense to me. And then you go looking in your repertoire of explanations, and you go, I've never, that doesn't have, I don't have any good explanation for why that's happening, and again, we can use the Einstein-Newtonian example because it's such a crisp, perfect example to show how this works, or what the difference is better. Because if it was just about more data, again, then why didn't other people get there? Why didn't that is not a good explanation for why that happened. So by looking at Einstein's creative act of going, aha, crazy idea. There's something called space-time. And yes, he stood on the shoulder of giants, right? So without Newton, there would have been maybe no Einstein, or maybe somebody else would have come along, or maybe it would have never come. We don't understand how creativity comes to mind, but we do know the environments in which it is more able to be to flourish, and that is in an open society of criticism and conjecture. So that's why when kind of the authoritarianism way of thinking, it halts creativity, because it literally tells you, don't ask questions, just do it. Or it tells you, no, this is because I said so, or because the dad or the mom or the teacher, the pastor, because I said so. It's an authoritarianism. They are afraid of getting that question asked because it could jeopardize their position of power and their position of superiority within that culture. But that's a cultural aspect. It has nothing to do with epistemology. It has it has nothing to do with the goodness of the explanation. So sometimes people think, for example, that of course Einstein makes sense because it's actually just Newton, but then like plus stuff. But it's not. It's a completely different model. If you want to program a computer to use Newtonian physics, you have to use things like the force of gravity. Well, if you program a computer to do relativity, you give it space-time. It's a completely different framework. It's the same as saying there was. I mean, it's not the same as saying, but it's like saying, oh, there was a god and then there's a better god. Like, no, it's you're invoking a lot of different things there. And that jump is a creative act. So to tie it back to your plane example, the first plane ever conceived was maybe inspired by the birds, because evolution has found ways to fly, and that is what they call like a I forget what the word is, but you have these features in animals that go across species, and it has a specific name.
Convergent evolution?
Yeah, something like convergent. Yeah, convergent characteristics or something.
No.
No, I don't know. So it's like insects can fly, birds can fly, some fish
Yeah.
can fly, right? So, but they're literally different species. So evolution has found a way to make them fly still, even though they're different species. And maybe the first humans were like, well, that's crazy, bird can fly, but then to go from that to building a Boeing 747, that requires the understanding of fluid mechanics, of air mechanics, of forget the engineering marvel that the moving parts of the whole thing. The very first plane that the Wright brothers built is in theory the same as the Boeing 747. It uses the downward force and the upward force of airlift, right? That's why the Formula One cars stay close to the ground, because they have reverse lift, and they push them to the ground. But you need that first human to go, like, well, they need to be interested in it. They need to be motivated to build something that can do that. And then, they need an idea. So they will have an idea, and they will say, maybe the first one tried feathers like a bird and they died. So, that knowledge is gone.
Yeah.
Then the second person will say, saw that person do that. Like, it can't be that one. Let's try even bigger wings or something. Let's try to do even, flap it even harder, because that's what the birds are doing. And then that will clearly get you nowhere. Because the anatomy of birds are completely engineered in a way for their body to do that, which is super complex in itself. But we cannot do that with flapping stuff. We don't have enough power to do that. So that won't get you there. So just continuing on how birds do it won't get you to a plane either. So you have to literally create a model of how does this thing work. And the first person has to go, oh, maybe they saw a leaf flying and they had an idea that the leaf is going through air, because you need the concept of air first, right? It's not obvious. It's obvious to us now because we're taught all these things, but the concept of air and flowing and going through stuff, and that leaves actually are taken by wind. Like I mean, how much we forget how much assumptions are packed into that are so baseline to us now, but aren't necessarily so in other cultures that wouldn't have had the all the knowledge given to them in the school system that I agree could be better, but did teach us a lot of good things as well. I don't know if that's hitting home the distinction here between you need an explanation, you need to try it to see if it works, and then if it doesn't, you need a better explanation. So yeah, the plane example is it's fantastic that we can have iron things flying through the sky. It's crazy, but it is how our universe and how aerodynamics work. And somebody was able to conceive of the theory of aerodynamics, and that is the most profound thing ever, that you can create the theory of aerodynamics and then actually use it to create the plane, right? So first comes theory, and then comes application of the theory.
Yeah. I think to circle back to what we were saying early, I think the book of nature, or data driven first, that's kind of way that we're taught also science works. But I think what you're saying, or what the book is trying to say, that's necessarily not how it works. If we take the Wright brothers of the plane, how did they come to their first working plane? By experimenting, exploring a bunch of ideas, not by measuring data and then just applying that to something, then suddenly they had a plane. So it was the ideas first, testing, and then came the data. So if we bring that to the Einstein part, well, there was the data, but did not lead to his new theory. No, he had the idea. He was the first to think, wait a minute, maybe it works completely different. And he had some ideas and then tested it. And from there came then the models, the data, and so on.
Yep.
So, but I think that the profound insight in here is that we are so used to relying on data, and science equals data, and then from the data comes the rest. That's not necessarily true. And especially, I would say, like breakthrough science and innovations, it's not the data first, it's the idea first. I think that's like the profound insight that you're trying to communicate.
Exactly. And the funny thing is that you're not doing it, even though, let's say, you would still work from a model where you think you're reading Book of Nature, and then you're somehow deriving theories, right? You're still not doing it, even though you think you're doing it. It's like, let's say Einstein thought that way. Like, it's not that Einstein wasn't necessarily aware of the Deutschian conjecture of it's conjecture criticism, and that's how knowledge works. I don't know, I haven't read up enough about Einstein's own thoughts about that, but the brain is, as you know, is often unaware of the thing it's doing, and it doesn't necessarily change that the fact that innovation is still done. I think it's just it can be done better with the understanding that that's how it works. That makes sense.
Yeah, exactly. It's good that you showed the picture of the galaxies and the stars, because I hadn't seen that before. And the first thing that I thought went to mind is, it's like a black and white photo of the peel of an apple or something. That is what it looked like. So now I understand better what you say. Imagine the amount of knowledge that it takes to be able to just give an explanation of what it is that you're seeing. It's just a bunch of black dots on a white gray background. And it could be anything without any proper knowledge. And the amount of knowledge required to explain, that's a planet and that's a galaxy, is just immense. And considering the amount of knowledge for such a small picture with just some black and white dots, I think that's another profound insight.
It's like the cork champagne example that Deutsch uses as well. This has more to do with the explanation needing to be of a different mode, a different level of what it's trying to explain. So, for example, he uses the there's in every like MIT lab or something, there's a bottle of champagne, and that bottle of champagne opens whenever a new discovery is made by that team, right? So a profound new discovery that that they've tested and that somehow tracks to reality. So let's say this is a hypothetical situation. You're an alien and you see that bottle of champagne opening. How do you explain that? Just by saying, oh, the gas laws, like cork opens because the bottle of champagne has pressure inside and therefore it opens. Like you're describing then indeed on a mechanical level, you're describing what's happening, but you're not explaining why it's opening. So let's say the latest discovery was a quantum event, so in order for that alien to be able to explain why that ball opened, they would have to understand the entire human civilization up until that point, because quantum is our best understanding currently of anything. So that's what I mean. Like you need a different level of explanation.
Of course, yeah. And then there's the other explanation. We talked about it in the previous episode as well with the copper atom in the statue. Like the cultural value or like the traditional value that we assign to opening a bottle of champagne for a special occasion.
Awesome.
You can explain the champagne, which is a drink, which is rare, which is a luxury product, and then you can explain like the cultural traditional event of people opening a bottle of champagne for a special event. So I think that's another level of explanation that is required, and that has nothing to do with the science. You can also, we could open the bottle of champagne, which we did, I think, when your baby was born, which has nothing to do with scientific discovery, but the same special event, special occasion made us open a special bottle.
Yeah, I would say that's even an easier explanation to give, because you just need culture there, kind of. You just need baby born.
Exactly.
But in the event of a MIT lab, inventing a new quantum theory, you would need to be able to explain that quantum event through. So you would have to have knowledge of the most crisp, pristine knowledge that we have. And the copper atom was Winston Churchill, by the way, in London. And you would have to explain the war as well in that event. So that's one part of it, right? But the other part of it is even the act of observing requires explanation, and that's what this chapter is trying to hit home. So, for example, let me share my screen again because they have some more here. So
pictures of apple skin.
So here he has like what used to be like how they interpreted, or how the data came out, or let's say how the what the machine did to give the line here of, I guess this is, what is this, nanoseconds or something, or false colors. I'm not too, anyway, it has to do with even interpreting this line, right? Requires a vast amount of explanatory knowledge, because what are you observing here? If you are
no idea,
if you're you and me, you're observing a crooked line. If you're an astrophysicist, maybe you're observing here another galaxy.
Yeah, the I've never seen this before. The first thing that it reminded me of was like a music bar. So it actually would be a really funny exercise to show these two pictures, the pictures of the dots and then this, to random people and ask them, what do you see? What is your explanation for what you see? And I'm very curious to what crazy stuff people will come up with.
But people will use their own cultural and knowledge back, what they have available to them, and they will test it, right? And then they will your mind will start going, it will start going, wait, it's not the music thing. No, it's not the music thing, because I'm not seeing, what I used with the best explanation of a music chart. It looks different. And then you go into, what could this be, right? And then you start coming up with ideas, and that's creativity. You start literally trying to come up with an explanation of what you're looking at. So I think this is like a perfect example of that. Depending on who you ask, the observation will have a different explanatory framework associated with it, and the one will be more accurate than the other, in the sense that
Yeah.
it is what it's used for. Um, but it's you're equally accurate to say this is a line. The line is 15 centimeters long, and it has dots here that maybe are um, a measurement of a kind, right? You could say those things if you had, again, the knowledge of measurement, if you had knowledge of that in this case, back in the day, they used to print these things on those kind of papers, because let's say you've never even seen a paper before, then like, what is a grid? What is, maybe this is a fence? Like, it, again, it's just to say there is no such thing as observation without theory first. And that's what the
Yeah.
empiricists get wrong. They think it's just about the data, but there is no such thing as the data. There is the explanation of something, and then you can only start gathering data through a model.
Yeah. There's actually a new idea that pops in my mind right now, because
Mhm.
one of the points in the books is we don't observe reality directly. We
Never.
observe it to observations and data and machinery, and we're looking at ink on paper or pixels on a screen. And I always thought it was, yeah, indeed, that makes sense. We don't observe it directly. We need stuff in between, like machinery, equipment, whatever, to be able to observe it, because we cannot really make out a galaxy with the naked eye. We need equipment for that. But what I think it means now is that it goes further than equipment and so on. Yeah, we don't observe reality directly. There's not only equipment in between, but there's also our explanation, our interpretation in between.
Well, there's your eye in between. There's your optic nerve that makes whatever you have on your eye go to your brain. Then your mind processes it, and then it gives you something. It gives you an explanation. So it's even like all what you said, yes, but it goes even deeper than that, because you cannot, let's say, observe without explaining the observation first. It is
Yeah,
impossible, because reality is infinitely complex, and you're only trying to solve a problem, right? So you're trying to solve a specific problem, and yes, we are part of reality. Right? You can interact with it, um, and you can test it to a certain degree, but you will only do so in the way that it solves your problems. Like, we don't see, for example, was it like infrared, right? We don't see it, but through the explanation of wavelengths, we can create machinery that can then detect it, right? But we needed the explanation of wavelengths first before we could create a machine that could discover it. So it's not like we had the machine and all of a sudden, whoa, shit, there's infrared, you know?
yeah, exactly.
Um,
Yeah,
you need to build the machine to do something specifically based on a model that you want it to do. Um, and yeah, that's indeed a very profound insight that I also, it took me, and I still struggle, because our brains do it so quickly, right? Our brains do it so seamlessly. They make it feel like there's nothing going on almost, but what you're doing is a very, very complex, comprehensive, constant explanation game. You're constantly explaining away things all the time, and then refuting it, once the reality doesn't match to that explanation. Like even the astrophysicists way here, like in the past, they were looking through their big, telescopes and lenses, and even that required a lot of knowledge about how lenses work, and how, then what you're looking at, you're still looking at, maybe the magnified thing, and then all of a sudden you see, oh, it's not just a smudge, it's actually a, it's a more like
a candle.
More. Yeah.
Well, it's the shape of a candle. Wow.
Yeah. Well, again, like you would only have the idea it's a candle if candles existed, right? Because somebody invented a candle. So
yeah,
again,
just imagine that
yeah.
we will look through a telescope and we actually see a candle in the sky. I think that would be hilarious.
You have to explain it. You would have to explain why a candle.
Yeah. Yeah.
So it's still the same thing still applies. Let's say the creation of knowledge goes through a conjecture and then criticism against reality, and then the best one that works for your problem stays until you find a better one, or until that one's not useful. I mean, useful in a certain domain case, because then you have a new problem and then you need a new explanation. So that's kind of like with Newton, it explained a lot of stuff up until certain points, and then you need something new. And then you say goodnight, right, to Newton. You say, now it's Einstein, and same will happen to Einstein's theory as well. Something better will come along that will debunk it. Maybe gravity becomes a force again. Like it's possible. It's possible that, or well, that's a bad explanation, but yeah.
Well, probably not. A lot is possible, but probably not. What you're saying right now brings us to the final point that I would love to have discussed. You say, okay, Einstein debunks, and probably in the future there will be a better explanation, being even a better explanation for general relativity, of course. And that's a bit the point of the title of this chapter, I believe. It's called Closer to Reality. In my interpretation, is because there is always a better explanation that will get you closer to reality. But of course, the title of the book is The Beginning of Infinity. So there's an infinite amount of better explanations. So you will never reach a final explanation. There is no such thing as a final model, a final explanation. The best possible, the maximum amount of possible knowledge. There is always more. And the way I like to envision it is like, I remember when we were in high school, we had to learn about graphs and limits, and you had the limit going to 0 or any other number, and the graph would edge ever so slightly closer and closer to 0, but never reach it. From a zoomed out point of view, it looked like it was at 0, but if you zoom in, it's not, and it always goes closer and closer. So that's a bit
like
how I
asymptotic.
Yeah.
Well,
yes, yeah, exactly.
Yes, but you have shift your mindset 90 degrees this way, because it's asymptotically approaching infinity.
Yeah, going up.
Yes.
More and more.
Yes. In this almost shows that in your mind you would say knowledge is decreasing almost, in a sense, or something.
No, we can flip it.
Yeah,
that's fine. But it's a bit how I envision it. So let's say that Newton is at that point 3. It's pretty close to reality, but not fully. And then Einstein come along. It's a big leap, and maybe you jump from 3 to 6. So now you're closer to reality. But we're still waiting on the next thing. Maybe there's already an explanation out there. I don't know. That will get us from 6 to 7. But if we look at this from this point of view, that also implies that it gets like harder and harder, because you need to have more knowledge, even more profound insights to get closer to reality.
What is harder about Newton coming up with gravity versus Einstein coming up with space-time? Why is that harder?
No, let's imagine they're probably equally as hard. But if we go back to the old Greeks,
define hard. Like, what makes it hard?
Maybe the amount of knowledge required. Let's call it like that.
I disagree.
Okay, and why that?
Because Newton created new knowledge.
Mm-hmm.
It didn't use Newtonian knowledge at all. It used new knowledge. Same as, like you said, the ancient Greeks, they had idea of Pythagoras, right, which was also new knowledge. So we definitely keep using what's useful, but there is no such thing as a harder knowledge.
Yeah, I understand what you mean.
Yeah. Okay, sorry. Go ahead with the.
No. That was it. I understand what you mean.
So I said, yeah, I get what you're trying to, from an analogy perspective, trying to get at, but I would say how I think of it is more like branching. You start with like maybe like let's say the first piece of knowledge in this in this analogy is like a branch, and then it branches in 3D out to like 5 more, and then all those branches get again more branches and more branches, and it's like, you know, the tree in the ground, but then on its head and upwards.
Up.
Yeah. That's how
You
I see
envision it more like the tree of knowledge. That infinitely growing tree.
Infinitely growing
exactly.
tree. Because
it's interesting.
You have different ways to latch on to reality. You can try to come at it from different angles, but we're always trying to solve a problem. That's what gets you there. You know, if so, problems are central in this philosophy, because without a problem, why even consider a solution? And if you can't even talk about your solution because you live in an authoritarian culture, then you will be shamed and you will not be heard, and that new idea that you had, will not reach the cultural knowledge, and it will die. For example, right? So, which should happen. So that's why an open society where criticism is valued is a better one for the growth of knowledge, because it allows it to freely be tested and freely be discussed without shame and without cultural stigmas, if you will, and dogmatic ways. One of the quotes I have open here is from Einstein, which is also a very profound one, I felt, and it reads as follows: "There could be no fairer destiny for any physical theory than that it should point the way to a more comprehensive theory, in which it lives on as a limiting case." So Newton, right, is still useful. It lives on as a limiting case. Einstein overturned it. It's literally wrong. But it's still useful. We still use it to go to the moon in its limiting case. So every solution has its scope, if you will. And Einstein just explains more. Einsteinian explanation is a more deeper explanation. It does a lot more than what Newton did, because any model that we have with Newton wouldn't be able to give us GPS, right? Because it wouldn't work. So the Einsteinian model is deeper, and you'll see that with any better explanation, it often is a more deeper way. It actually bridges other domains often, if you will. It doesn't make things more complex. Better explanations actually simplify things.
Yeah, I think that's a beautiful insight and a beautiful quote. Yeah. All right. Those were all my insights from the second chapter. Is there any other last thing from the chapter Closer to Reality that you would like to bring into the group?
I think maybe to go back to your error correcting interpretation. Let's end with the the cluster of galaxies here.
With the apple skin.
Yeah. So error correcting is just, getting closer to reality is a way to describe it, and it's a good way, because you're always getting somewhat closer, but now I understand a bit. Your in your graph, reality is the zero or something, right? And you're always
Yeah.
getting closer. Yeah, I now understand. I would say that probably Deutsch used that language to appeal to the empiricists, because sometimes you need to use language that is familiar to get people on board with your new ideas. And you see this often. The religions have understood this very well. If you want to replace a religion with another, you always have to retain elements of the previous religion, or the people will reject it. That's why the very first churches in Rome have elements of the heathen temples, where you had, like, openings in the ceilings, right? Like the domos, right? The very first one has like an opening. It's one of the most famous ones in Rome, which is one of the first churches ever built, because they understood, if we break too quickly with previous heathen traditions, the people will reject it because the change has come too fast. So you need to retain some elements. And I think any smart person trying to help further his cause will try to appeal sometimes to the other side by speaking in their language. And I think that's what he's doing here, because he will say as well, and obviously I cannot speak for him, but after having seen and read much of his stuff, I think now I've come to understand he actually would mean um, um, always closer to a better problem, um,
Yeah.
that will solve the next problem, and so forth. So reality is out there. It's infinitely complex, and we only decide which part of it we try to understand based on problems we encounter. Um, which is a good thing to do. Like, you want to solve your problems. I think a lot of, like, people with depression, they become depressed because they start solving problems that aren't their own, because they have misaligned their problem sets with themselves, in a sense. So the error correcting part I see as kind of like you want to swap out, you want to incrementally get better. You want to do it incrementally, and you want to do it quick. Because if you don't do it incrementally, like my religion example, you get rejected by society. So by swapping it out and error correcting it in little increments, everybody kind of is on board, because you're not changing too much too fast, or you're not changing yet too much in one time. So you want to change things quickly, but incrementally, and that way we keep building further on that body of knowledge that we've created. But there's no law of physics that says that it will happen. So I think as you read further now and you go into the definition or the concept of optimism that Deutsch has, is he says it's possible, right? Because whatever is not prohibited by the laws of physics is possible, is one of my favorite quotes of his. Where is it here?
There, the one on the left. It's
Yeah.
the first black row, the one on the left. Yeah, that one.
But it's not forbidden by laws of physics, and is achievable given the right knowledge. So there is no law of physics that prohibits us from making progress, but it also doesn't say we have to make progress. It just says it doesn't forbid it. So that's why it's important what we choose to do, that we choose to make progress through a open dynamic society. And then his principle of optimism has to do with that. It has to do with the fact that it is possible, guys. We can make progress, but it isn't necessarily so that we will. The Roman Empire also ceased to exist. There's, there's all kind of cultural reasons why we can also stop making progress, and even go back into the old ways of the dark ages, for example. That was one of those prime examples where we were stuck for basically changed, right?
Yeah, for a really long time. There was little to no increase of knowledge until the Enlightenment came.
Exactly. So yeah.
All right. Is this a sneak preview of the third chapter?
Yeah, let's go for it.
Right. I know that was a question. Is if this part is a sneak preview of the third chapter?
Oh wait, what's the third chapter again? We have the book here. The Spark. So the Spark speaks about mostly, basically like the optimism is part of it, and that progress is possible, that problems are soluble. That are the main concepts of chapter 3. So that's a very cool chapter 3.
All right, cool. I'm looking forward to reading the third chapter the coming 2 weeks, and we will continue talking about it. So our next episode will be about chapter 3, where I assume we will be talking a lot about optimism.
As we should. Exactly.
All right, cool. I want to thank everybody for tuning in again, and let's see you next time where we continue with chapter 3.
Thanks, everyone. Thanks, Erik.
Thank you. All right, nice.
Ik
Ik heb meer het gevoel of nu hadden